So this is our group members. First, Siti MASHITAH binti Harun. Matric number is AE230033. Me, Nurul Farah Wahidah binti Narman. Matric number is CE230005. Muhammad Ridhwan bin Muhammad Rahim. Matric number is CE230022. Muhammad Syahmi AIMAN bin Muhammad Ali. Matric number is CE230053. And Najmi Farha binti JAMIL. Matric number is CE230063.
Hi, my name is Muhammad Ridhwan bin Rahim, and my matrix number is CE 2322. This is our methodology for our group project, which is for the theory parts. A periodic function is expanded into a complex exponential sign as part of the approach, using the Fourier series representations to its advantage. This method expressed the periodic signal as the sum of complex exponentials. The frequency components of the signal are revealed by the coefficient of this exponential. Low pass filter is used to concentrate on the lower frequency components. The tools that we use for our group project, which is MATLAB and Proteus. And why we use MATLAB is because MATLAB is the primary tools in this project methodology, which address predetermined objective. MATLAB is a great tool for developing, analyzing, and validating such as approach because of its flexibility, strong numerical capabilities, and the capacity of MATLAB to smoothly integrate the data analysis, mathematical methods is what motive the use of the program. And for the Proteus, which is we use because Proteus a popular electrical design automation EDA program for creating, modeling, and testing electronic circuits is called Proteus. It provides an easy to use interface for building circuit design, arranging parts, and digitally connecting them. Its ability to simulate circuit behavior under many circumstances without requiring a physical implementation is one of its primary features.
Assalamualaikum warahmatullahi wabarakatuh. My name is Siti MASHITAH binti Harun and my matric number is AE230033. So here are the coding for the MATLAB for the question 1 for the signal in time and frequency domain for the 5, 10 and 20 harmonics. So here are the name of the group members for the group 2. So the first thing is we need to initialize the parameter. In the right side, I already have the comment to make the more to understand. And then the second is we need to freeze series initialization. So we have amplitude, number of harmonies, and the DC component. So we also have to declare the plotting figures for the 5 harmonic, 10 harmonic, and 20 harmonics. And also we will have a 2 graph for the figure 1 and figure 2. So in figure 2, we have the frequency domain for the original, low pass filter, and the frequency domain filter. And the last is output of the filter was original. So then we need to declare the low pass filter setup. So here are the codings. And then we need to compute Fourier's coefficients. And then we have the Fourier series computation and filters. So when we need to declare everything in the MATLAB. So here are the 5, 10, and the 20 harmonics. And then the last is we have the final time domains in the plots. So it's to make the difference for the time frequency domain. So if you want to run the MATLAB, we need to separate the 5 harmonics and the time domain because if we combine in the same coding, we will not get this answer. So we need to separate first. So the result I will show for the next step. Thank you. So here are the difference of the 5 harmonic, 10 harmonic, and the 20 harmonics. If you guys see for the 5 harmonics, is the shape, the wave is smooth and resemble a low frequency red signal. And the 10 harmonic is more, the waveform is become a more complex. And the 20 harmonic is become a more complex and the shape is become a square wave. So what I can conclude is the more for the more harmonics you take, the shape will exactly same with the square wave. Okay, for the frequency domain, so we are analyzing how a low pass filter works to clean a signal by removing high frequency component. For the first graph is frequency domain original. The graph show the original signal in the frequency domain. Peak represent the difference frequency present in the signal. And then for the second graph is low pass filter response. Here we see the low pass filter in action. It keep low frequency on the left, and while gradually reducing high frequency on the right. And the third graph is frequency domain filter. After applying the filter, the high frequency are removed, leaving only the low frequency component. The fourth graph is frequency the fourth is filter versus original signal. So finally is the time domain. The original signal or the original for the red one is noisy. The filter blue is smooth because the high frequency noise is gone. I think that's all from me. Thank you.
Assalamualaikum and hello everyone. My name is Farah binti Jamil, and I would like to explain about the low pass filter in this project. First, we need to know what is low pass filter. A low pass filter (LPF) is a tool or system used in signal processing to allow low frequency signals to pass through while blocking or reducing high frequency signals. And at the side, we have the manual calculation of low pass filter. We have been given the F0 and FC. F0 equal to 260 kHz, while FC equal to 930 kHz. And then we need to find the HF or frequency domain. While using this formula, 1 over 1 plus J F over FC. And then substitute the value into the equation, and we have obtained the final answer for this low pass filter, which is equal to 1 over 1 plus J 26 over 93. Now I'm going to show you the coding for low pass filter with frequency response characteristic in MATLAB. Okay, these are my group members, including me. And on line number 10, we have the low pass filter parameters, and we have the R that we assume equal to 50 kilo ohm, and the capacitor in Farad. The given F0 and FC. F0 equal to 260 kHz, while FC equal to 930 kHz. Then on line number 16, we have the frequency domain calculation, where we assume Fs for the signal. And these are the formulas. Okay, so we have two figures in this coding, this MATLAB. For figure 1, we have the low pass filter in time domain. It will come out or show the result for low pass filter in time domain. And then in figure 2, we have the low pass filter in frequency domain. Okay, now I will run the coding. And then we have obtained two of the results for this coding. First, in figure 1, we have low pass filter in time domain. This is the graph, and this is the graph for low pass filter in frequency domain.
Assalamualaikum and hi, my name is Farah binti Narman, matric number ECE 230005. Today I will present about the manual calculation of circuit low pass filter. And given FO equal to 260 kHz and FC equal to 930 kHz, we assume C equal to 50 picofarad, and for the formula of FC is 1 over 2 pi RC. We calculate the R equal to 1 over 2 pi FC, C, and we get the value of R equal to 3422.96 ohm. So this is the circuit for circuit low pass filter. For the first, we use digital oscilloscope, signal generator, resistor, and also capacitance. Digital oscilloscope used to analyze the circuit. For signal generator, used to combine the waveform. So we insert the value of resistance 3422.96 ohm, and also capacitance 50 picofarad, and we run to get the waveform.
Hi, my name is MUHAMAD bin RAHIM, and my matrix number is CE 2322. And this is our coding for define lower and higher duty cycles, which is, you can see that the first I define the parameters, which is samplings, frequency in hertz, time vector, 1 second durations, and signal frequency in hertz. And then I generate PWM signal with different duty cycles, such as 10, 20, 30, 70, and 80 for the percentage of duty cycles. And then I plot the PWM signals and I generate in a square wave with the duty cycles. And then I run it. As you can see, the result on the right side, which is the signal is increased. And for the conclusion of my result, which is the duty cycle of a PWM pulse width modulation signal, refers to the percentage of time the signal remain high on during one cycle. If the duty cycle is low, such as 10, 20% or 30%, the signal is on for a shorter time and off for a longer time within each cycle. As a result, less power is supplied to the load. This is useful for application where reduced power consumption is desired, such as LED dimming, low level control fan speed, and energy conservation in electronic equipment. On the other hand, a high duty cycle such as 70% or 80% indicates that the signal remains on for most of the cycle and off time is short. This leads to the higher power delivery and is beneficial for applications that require more power, such as running motors at higher speed or increasing the brightness of the lighting. In summary, lower duty cycle have a lower power output and are better suited for low power operations, while higher duty cycles have higher power output and are best suited for the higher power requirements. PWM has become an effective method for power management in a variety system because adjusting the duty cycles allow power to be efficiently controlled without changing voltage or current. Hi, my name is Muhammad Ridhwan bin RAHIM. My matrix number is CE 2322. This is the effect of having lower or higher duty cycles, which is the duty cycles of a PWM signals determines the on or off ratio and average power output, which is first 10% duty cycles is for lower output. It's suitable for minimal power application like dimming LEDs to low brightness or slow motor control through the slower system response. For the second, which is 20% of duty cycles, slightly higher power used for steady low power tasks like moderate LED brightness or slow motor speeds, balancing energy, saving the improved responsiveness. And third, 30% duty cycles, which is moderate power, ideal for balanced energy efficiency and performance such as medium motor speed or lighting levels. 70% duty cycles, which is we use for high power output, ideal for performance focused tasks like fast motor speed or bright lighting, but with increased energy consumptions. And lastly, for 80% duty cycles, is very high power, suitable for maximum output application like heavy duty motors or high intensity lighting with potential for high energy use and overheating risk.
To wrap up this project, this study integrates theoretical derivations, MATLAB simulations, and practical experiments to provide a comprehensive understanding of exponential Fourier series and low-pass filter performance. Our key findings include Fourier series effectively reconstruct signals with validation in both the time and frequency domains. Then low-pass filter, significant variation in frequency response when duty cycle range from 10% to 80%. Overall, this will emphasize the importance of combining signal processing techniques to address real-world challenges in electronics, telecommunications, and control systems. Thank you for your attention.